Okay, I guess we can start. And before we start, let us start by introducing ourselves. As Nikola mentioned, I'm Özer Dilektaşlı. I previously worked in a mobile gaming company, and currently I'm working at Havelsan as software engineer, and in serious games team. And that's it, I guess. What about you, Oğuzhan?
Hello everyone, thank you Özer. Let me start by introducing myself. My name is Oğuzhan. I am from Turkey and I work as a software developer at Havelsan. I work at simulation and autonomous platform technologies together with my team and Özer. In our team, I'm mainly responsible for development and system design, especially for our training simulators.
Okay. You see our agenda here, and first we'll talk about our project introduction. We'll try to tell you why did we build this system, and we'll go with managing sessions in real time, connecting Redis and a third-party library with Unreal Engine, building the simulation environment, and how did we actually manage the entity's data. And as a conclusion, we'll talk about from communication to synchronization. And before we start, let us talk a bit about Havelsan. Havelsan is basically a defense industry company located in Turkey and Ankara. It mainly works on integration and training, platform management, autonomous systems, and simulation systems. And today, we are going to talk about the infrastructure we built and that is used in more than one project. In most of the simulation projects we work on, the main purpose is simulating a vehicle. In our case, this is a tank. When you consider a tank, it consists of multiple roles like driver, gunner, and commander. Thanks to that, whole tank crew can experience the same realistic scenario simultaneously. We enable trainees to improve both their conditions, coordinations between roles, and their decision-making processes in different conditions. And now, once we simulate the roles and the scenarios, let's talk about how do we manage these scenarios with instructor operation systems, in short, trainer consoles, actually. We have two trainer consoles. One of them is 2D web-based instructor console. It's portable and allows trainers to access quick scenario control. We'll talk about that later in detail, actually. Other one is 3D Unreal-based instructor console. Both allow us to control and monitor the same simulation. And let's see a quick demo. What do we have, actually? You see our 2D web application and one of the clients we have. Once the vehicle moves, its position is updated simultaneously to the web application. And we can even see its properties and monitor the properties, actually, like the speed, its location, as I said. And also, we can give malfunctions that a vehicle can actually have in the real world. Once we gave those bunch of malfunction, the vehicle is not able to move anymore, and you can see its speed is decreased, and we can even set its fuel level or etc. And you see our data flow here. 2D iOS sends data to 3D iOS. In that case, the 3D iOS is actually an Unreal server, and the Unreal server and 3D iOS distributes the incoming data from 2D iOS thanks to the replication to connected clients. And the critical thing here is that all those client and server and 2D iOS also should be in the same session. If any of them goes wrong state, whole simulation can actually break down. And that's where our session management layer goes in. And now Oğuz will talk about how do we manage sessions in real time.
Thank you, Özer. One of the main challenges in real-time communication is managing sessions. We need to know who is connected, how long have they been active, what happens if someone disconnects. Just like in the matrix, when Neo connects to the system, the matrix needs to recognize him, initialize his session, and keep him active as long as he is inside. In the same way, our session manager tracks every client and ensures continuity even when connections are unstable. And since this is also an educational simulator, our infrastructure doesn't just manage the connection, it also generates reports, so we know exactly how each student performed in their training scenario. Now that we understand the importance of session management, let's explore why we choose a web application. First of all, ease of maintenance, faster development cycle, lower cost compared to Unreal development, larger developer pool, remote and multi-PC management. Since this is an educational simulator, the web makes it possible to control and monitor training sessions from different PCs or even from different locations. Having discussed the advantages of web applications, let's now shift our focus to messaging infrastructure. We have two options. They are UDP and PubSub. But why have we chosen PubSub? At first, UDP looks simple. One server, multiple clients. But notice the server must send separate messages to every client. This works for one-way communication. But what if we need responses back? On the right, you see PubSub. The publisher sends one message to the broker, and all subscribers get the update instantly. The PubSub mechanisms provides the ability to publish messages to specific channels. This feature allows subscribers to only subscribe to the channels they are interested in. As a result, the data flow becomes more targeted and efficient. This enables system to quickly access the information they need and enhance the overall efficiency of the system. Now, why is this important? Because in our case, communication is not just one way. We need two-way communication, and we need event-driven updates. With PubSub messages flow in both directions, publisher to clients and clients back to the publisher, always through the broker. This guarantees stable and scalable communication. And it's not just raw packets. What we send are structured messages JSON payloads. For example, speed 50, that's a real-time state update. Another one, firing mode ceasefire, that's an action command. Or act through a client acknowledgement. PubSub ensures every subscriber instantly receives the right update without building messy point-to-point connections, and we used Redis to provide PubSub mechanisms. Let's inspect what is Redis. Redis is an in-memory data store. It's extremely fast, reliable, and already PubSub out of the box. So, Redis is not just a database, it's also a real-time communication layer. And why Redis? Because we needed a central hub, a message broker between our web application and Unreal Engine. This reduces latency and simplifies our architecture. But Redis is not just a single pipeline. We can subscribe to multiple channels at the same time. For example, our system listens to heartbeat channel to monitor who is alive and connected. At the same time, we listen to the virtual element channel, which tells Unreal to create or update tanks, aircraft, or any entity in the scenario. This is what we call event-driven updates, instead of constantly polling or checking states. We react only when an event arrives. That way, Redis helps us message our states in real time, scalable, and efficient. So, in practice, Redis became our message router. It connected different programming languages, handled two-way communication, and kept everything in sync. Thanks to Redis, we achieved real-time responsiveness without building messy point-to-point connections. Remember the JSON messages you saw earlier? Redis is what carries those instantly from one side to the other. On the back end, we integrated Redis using Java libraries. We implemented publisher and subscriber clients that exchange JSON messages through Redis channels. For example, when a user clicks a button on the web application, the backend publishes a JSON message. Redis instantly delivers this message to Unreal Engine, which then reacts in real time. Now, Özer is going to some information about Redis in Unreal Engine.
Okay, thank you, Oğuzhan. And now let's talk about the journey about how did we integrate Redis into Unreal Engine. We'll inspect our implementation journey in 3 headlines actually. First, we'll talk about bridging cleanly. This part will be all about introducing a third-party library, in this case this will be a Redis library, into Unreal Engine. And then we'll talk about hiding the unnecessary. We'll try to expose only what's relevant. And finally, we'll talk about encapsulating the complexity. We'll try to provide a clean and easy-to-use API to the developers. And let's start by bridging cleanly. As you probably know, Unreal actually doesn't provide a native Redis library. And building it from scratch is complex and costly. If you try to do it, build it from scratch, you'll probably handle a bunch of things. So we have decided to use Redis C library. It is an open source library, which is commonly used also in C family languages. Once you have the library, it's actually a messy way to directly copy and paste all the files like header, C, and all other files. Instead, Unreal provides cool features and useful features to introduce a third-party library with Build.cs. Before we dive into Build.cs, let's talk about how separation can actually bring clarity. Instead of putting everything in your project's main Build.cs file, I highly recommend that creating an external module. So you can put all those internals there and you can separate the modules. If you want to use it with different modules or even with different projects, you can just use that module that you externally created. Also, if the library have new updates, you can just update the module and everything will be updated. And now let's dive into Build.cs. You see, this is really a basic Build.cs file here. First thing I want to mention is marking module type as external. This will tell Unreal that the module is only include third-party things like the header and bunch of stuff. So Unreal will skip compiling them and your compilation speed will be increased. And then we have public include paths. This allows you to include shorter paths actually. Without this one, you would have to include full path of the file where the file is located. Once we are talking about third-party libraries, we also have platform-specific files like DLL and SO. We can also check our target platform with target.platform. And then public additional libraries allows you to introduce the headers or internal functions that the library has. Without this one, you will have unresolved symbol errors. And finally, runtime dependencies allows you to automatically copy and paste the desired file into your package project. You can also use this one if you have like JSON, XML, and any other third-party file. So that was actually it about the Build.cs. If you do this setup, you can use any other third-party libraries actually. And now let's talk about what do I mean by saying hiding the unnecessary. Most of the communication libraries has the functions, classes, or variables can actually be simplified in the, let's say, the library. You can wrap into single one, and if you have the source code, source files, you can use tools like CMake, and you can rebuild all the files you have. Thanks to that, you can use the modified library. And finally, let's talk about encapsulating the complexity. So basically what it is, it's actually an adapter layer between high Redis internals and Unreal Engine. What it does, it simplifies sending, receiving, publishing, and any other native functionalities inside it. How it plugs in, because this is also an external module, you can use it for your project-specific needs with subsystems or blueprint function libraries, let's say. And finally, how it stays safe, we try to protect you against race conditions and synchronization problems. And now, let's talk about how you can actually provide integrity and safety of those communication libraries. Most of the communication libraries consist of the logics and functions that are blocking by context default. The situation is like this. Let's assume we have a message that is responsible for changing the color of the mannequin. Unfortunately, you will only be able to see the updates when the message is received. And this is not the result you want, probably. To provide this, you need to handle those functionalities in an async way. Once you provided asynchronization, your game thread will finally be free. And now, let's talk about how you can provide asynchronization. Although there are few ways to provide asynchronization, we have finally used F-runnables. F-runnables are basically separate threads that you can separate your game logic and the other things. The run method inside it will run infinitely unless you say the opposite. Since it's in the separate thread, your game thread won't be affected by it, the logic inside it. It also provides lifecycle control functions like create, run, and stop. And also, you can give them name and priorities to dedicate the resources. There's a problem. You should always be careful with threads. Without proper lifecycle control, the orphan threads will multiply like Agent Smith that are waiting for a chance to crash your simulation. And let's see how you can actually track the lifecycle. I recommend that always give your thread a descriptive, unique name. In that way, you can log its creation and destruction like in constructor and distractor. Once you observe a problem, you can open that log file and see if the thread is created or destroyed correctly. The other thing is I want to mention about the resource monitor. On Windows, there is a program that is built in called Resource Monitor, and that shows all processes and its corresponding thread counts. While checking the thread counts, you can actually see if the thread is created or destroyed. And now, let's talk about how you can actually communicate with F-runnables, I mean the separate threads and game thread. The threads and F-runnable often needs to talk with game thread. But remember, this is a separate thread. If you try to touch the game thread directly, you will face with conflicts, crashes, freezes, and unfortunately, race conditions. To avoid this, you can use async task. Async task basically schedules the job you want to be in the game thread, or any other thread actually. Once you schedule your job, since it's provided from the async task, it won't touch the game thread directly, and you won't have those crashes or conflicts or race conditions. There is also a problem while using F-runnable and async task. Async task can capture variables or even the dispointer. If the F-runnable is destroyed before the async task is executed, you will try to access a memory which is invalid anymore. So this is also the situation you will face with crashes or bunch of null pointer problems, actually. The situation is like diving like Peter here without no guarantee. Sometimes you may crash safely, but probably most of the times you crash hard. So this is actually how you can get those random and hard to reproduce crashes. And unfortunately, checking if this won't be work. Because by checking if this, in this case, the destroyed F runnable, you are still trying to access a memory which is invalid anymore. So there is a way if shooting web is safe or not with smart pointers. We actually don't capture the disk directly. We capture it with T-weak pointer. The method inside it, the pin, returns a valid shared pointer only if the object is still alive. That relies on your object's reference count, actually. In that way, you don't touch the you don't touch the memory directly. You touch the memory with reference count, actually. So now, I guess, it's safe to shoot our webs. We have just seen how Unreal communicates with Redis and synchronizes the data. Now, it's time to make that data visible and meaningful. Now, let's back to Oğuzhan.
Thank you, Ozar. In this section, we will build the environment. We will place our entities, set the teams and enemies, and create a space that can be viewed in 2D and 3D. This is the moment when the simulation starts to feel alive. The main reason we build a simulation is flexibility. Instead of one fixed scenario, we can create many different stations. For example, we can change the terrain, the weather, and enemy behavior. This helps trainees face new station and train safely. Our simulation is not static. It includes tactical terrain, dynamic AI units, and other interactive elements. This makes the training much more realistic. And here is how that looks in practice. Here you can see examples in 2D and 3D. Now we are creating a tank. We can name it anything, but its type is tank. Then we are adding other tanks, and they are AIs. This is our team. Here you can see the enemy tank. Now we are creating an educational environment. And now let's explore the entities. Here we have an AI tank. Its ID makes it unique, and it has name and virtual element type. Then we have property items. They show the current state, speed, altitude, team, demet status, and firing mode. This keeps everything in sync, easy to create with code. Now we have seen what an entity looks like, but it's the real power. The property items part is flexible and scalable. Now, let's see the training vehicle. Our message structure is strong because the property items part is scalable and efficient. For simple entities, it only shows speed and team. For a detailed training vehicle, we can add much more: malfunction data, fuel level, and sensor status. This way, we use the same format for every entity, no matter how complex. It keeps the system flexible and makes adding new properties easy as our simulation grows. Well, Özer, what happens in 3D now?
Okay, thank you, Oğuzhan. Let's talk about that one. In Unreal, we needed a way to manage entity data that is seamless, scalable, and simple. Our goal was to create a unified data flow that minimizes the overhead. In simulation, we are not just dealing with few values. We are actually dealing with massive amount of value, massive amount of data. The challenge is to make sure every piece of data is processed in the right place and at the right time. So let's see, why do we have massive amount of data? The mission system is one of the key reasons why data matters in simulation. It's not just about visuals, it's about replicating the real hardware behavior inside the vehicle. Every switch, LED, and screen you see here must have the data behind it. So the mission system becomes a digital twin of the real-world mechanics, letting you train and test as if you were inside the actual vehicle. And now let's inspect what kind of data structure and implementation we have. Instead of putting everything one big class, we separate the responsibilities into modules like movement module, weaponry module, and sensing module. This makes the code cleaner, easier to change, and add to new feature later on. We also keep our data in separate classes, not inside the modules themselves. These data classes actually act like mediators. Probably you have previously heard about the mediator pattern. And modules don't talk each other directly. They talk through the data classes. This way, we get a single source of truth and avoid duplicated states across the system. We also needed consistency by design, and what I mean is we needed to provide two features like late join and snapshot. Late join is basically lets a new player join the session at any time, and snapshot is basically capturing the state of the world and allowing to play it at any time as the trainer wants. And so, let's talk about how do we actually structure all this data. Everything actually starts with the server. Server basically calls the setter function of the variable. Thanks to replication, the data is immediately mirrored in the client with onRep functions. Once this has happened, we broadcast delegate in both sides, I mean server and client. Once the broadcasts are fired, the modules that want to get that update can notify with updates actually, thanks to broadcast and custom delegates. I think everything sounds clear and structured so far. But unfortunately, there's a problem again. The real challenge begins when raw.json hits the system. You see, this is what happens when you try to parse the incoming message manually. You have to write all data, and this means, in our case, big and giant if-else chains, because you have to write and check all the fields of the JSON to update the data. You also need to call the setter function manually, so this is actually not the thing you want. This looks so ugly and not maintainable, not extensible, and we need actually something more clever. Don't get me wrong, it works, but we need something more clever. So what if we could make all this generic? I mean, instead of writing custom setter for each property. Eventually, we have used one of Unreal's reflection system, F-properties. And let's inspect what F-property is. F-property basically stores the metadata class for every U-property. With F-property, we can iterate over variables dynamically and see what type they are. It can store name, type, offset, and custom hook functions of the variable. This is the foundation of Unreal's reflection system, and we can use it to make our architecture smarter and more generic. Once we know about the F-property, it's, I guess, time to create those F-property classes. And T-field iterator does the thing we want. You can iterate over the U classes and U properties, and it creates F-property classes for us. This gives us dynamic way to access data without hard coding property names or types. And let's see why F-property actually fits our system. We have already setters in place, and F-property lets us safely call them at runtime for any property with built-in type checks. This creates a clean, generic pipeline for updating the values. As I mentioned earlier, you can actually bind hooks to the F properties. In C++, you can declare the meta, setter, and getter, and you can write the function as you want to be setter or getter, the dotted lines here. And thanks to that, you will unlock the ability of using hasSetter and callSetter calls. So we can safely call property setters dynamically without manually wiring them one by one. Once we have actually bound our setters to the F properties, it's time to access those F properties at runtime. We have used tmaps. As the keys, we store the F properties variable name, and values, we store the reference of the F properties. Thanks to using of tmap, we achieve O1 lookup that is actually a very fast runtime. And if you wish to use arrays, it will a linear search, and you don't even know how will fast, and etc. We can read or write values instantly. Thanks to that, we don't have to handle pointers manually, and everything is reflection driven. And lastly, let's talk about how you can do when you do want to apply this for all the entities in the world. Basically, we have used map of map. Remember, always was mentioned, every incoming message has an entity ID. So we store the entity ID as keys here, and as values, we store the data map. Thanks to that, we can still achieve the F property over the entity, still O1 lookup. To sum up, what do we have? We resolve the actor by entity ID, get its property map, get F property reference, and finally, we call its setter. And let's inspect what did we achieve actually. Previously, you had to write giant if-else chains. Remember, we have massive amount of data. We don't know how many lines you have. In that case, we'll actually have hundreds of lines. And with unified property handling, I mean using F properties, we have the system like this. We get entity's reference, which is resolved by the entity ID, then get properties name and properties value. Once we get entities data map, we get properties reference instantly thanks to O1 lookup. And then we convert the data we wish to update to the void pointer. And remember, void pointer is the pointer type that you can hold all the references inside it generically. And finally, we call the setter inside the F property. In that way, we have a bunch of lines, but previous one was not maintainable actually. You can think of it like this. The old way was using a payphone. You would have to search phone book one by one, and the person you find the person you want to call and dial the number you want to call manually. With the unified property handling, it's like using a smartphone. You just type the name and press the call. It's fast, maintainable, and also extensible. So far, we have talked about on how those different systems communicate each other, how messages are sent and received. And now, let's go one step further and talk about how do we manage to keep these two worlds in sync at all time. To provide synchronization in both web and Unreal, we have implemented a same state machine in both sides. Thanks to that, we can guarantee whole simulation is in the same state. And let's inspect what kind of states we are. The init state basically initializes the session. It sends an initialization message to server and the client we want to be in the session. Once there's a problem inside it, it will stop everything and it won't return a success message. We manage this messaging with HTTP actually. So we can get callbacks instantly. So we can what kind of error we have. And then we go with run state. This is the state actually all communication system and all the simulation starts. We basically start the simulation here with run state. And once we are talking with educational simulator, we also allow to use, we also allow pausing the system. Once we pause the system, everything stops. Every messaging systems are also stopped. And we get the time dilation 0 here in Unreal, I mean. And there is no data flow between Unreal and 2D web application. Also, we resume the simulation, as you can probably imagine. And finally, we need to stop the session. So when we click the stop button, whole simulation instantly turns its initialization state, but server gets the active scenario to allow trainer to edit the new scenario actually. So we then go back to init state, and actually that was it. So thank you for listening us. This was all about our session here, our session today. Hope you can find something insightful for you. And it was great. It was a great honor to be on this stage and sharing the stage with Oğuzhan. And Oğuzhan, would you like to say something?
Thank you, Özer, and thank you for listening. Thank you.
Thank you for coming. It's too late, I know, but you are here. We are much appreciated, guys.